Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome each and every one of us to my channel and also encourage our members to kindly subscribe, engage us in the comment section and also ring that notification bell to be getting a number of updates that we do in mathematics, chemistry and biology and other related topics. Now in this specific discussion, I'm going to look at the concept of magnitude of magnetic force. And this is going to be following up on a number of discussions that we have done, particularly on the concept of magnetism, electric current, and magnetic fields. And this, of course, is going to cement on the previous work that we have done. Now, today we are going to identify a way in which we can quantify this specific concept of magnitude. And therefore, I'm going to give a particular, of course, a formula at the end of our discussion, how we can be able to, of course, illustrate or give this specific magnitude. Now, we're also going to tackle one question set or two, which are going to form our final bit of our discussion in this specific concept. Now, from our previous discussion, I had basically mentioned that the interaction between magnetic field and electric field are going to, of course, produce what we call a catapult force. And this is going to be realized due to the interaction of the two fields as I have mentioned. Now we had, of course, mentioned some of the experiments that were performed by, of course, some of the scientists, which, of course, led to this specific conclusion. And from the experimental evidence, of course, the direction of this particular force has been, of course, shown. And, of course, we're going to see that this is going to be assisting us trying to quantify this aspect of the magnitude of a magnetic force. Now, this is going to entail a few aspects which we have learned, especially concerning current and the length of a conductor, which are going to play a vital role in trying to assist us, of course, quantify this aspect of the magnetic force. Now, in this case, I'm going to look at this specific aspect using the particular illustration which I've given, of course, on the left side of the board in terms of this a particular figure. Now, in this case, I've given the magnetic field lines direction, which have been given pointing in that specific direction. So I can just give this one as this one. And then I'm going to have a carrying conductor, which is interacting with this specific magnetic field at an angle. Now, I've given this specific angle as theta. So this is going to be the angle of interaction between the magnetic field and the current carrying conductor, which is being given as such. And L is going to imply the length of this specific conductor given as such. And therefore, we're going to look at the relationship between this specific, of course, current, the magnetic field, and of course, the length of this particular conductor. And that's going to give us the magnitude as I've said. Now, from my experimental data, the force which is going to be developed from this one is directly proportional to the current and length of the wire. And therefore, that's going to give us the first relationship we are going to encounter between the catapult force, which is going to be, of course, realized due to the interaction of the two. And as I've said, this is going to be directly proportional to the current, which we can give in terms of this I, and the length of this particular conductor, which I've said I'm going to give in terms of that one, B. Now, also, we're going to see that the force is also going to depend on the angle between the direction of the current, which is going to be shown using this specific direction. And in this case, I've just given this particular angle to be theta given as such. And therefore, we're also going to see that the direction of the field is going to matter in this particular case. So therefore, we're going to see that there's going to be also direct proportionality between this specific force and the magnetic field, as we're going to see. And of course, the angle between this specific field and of course this current carrying conductor, which we have shown in terms of now in this case we are going to have this particular relationship, and therefore that's going to give us our first equation showing the relationship between current, length of the wire, the magnetic field, and the angle of interaction. Therefore we shall have this equation given in terms of F is equivalent, which is a force is equivalent to the product between current, the length of the conductor, the magnetic field, and the sine of the angle, which is theta, the sine of the angle between this magnetic field and the conductor, and therefore this is going to be giving us as such. Now, from this one, we are going to see that the extent to which this specific angle of interaction is going to be shown is going to depend on of course, the force is going to depend on this specific angle, whereby we are going to achieve a maximum force which we can give in terms of force maximum when this specific theta is equivalent to 90 degrees. So therefore, if it's going to be perpendicular to this specific magnetic field, then therefore we are going to achieve the maximum force. But as we know from the trigonometric ratios, the sine of 90 degrees is equivalent to 1. Therefore, we can find a force maximum at this specific point, given as the product between current, length of the wire, the magnetic, force which is going to be given as such. And then we are going to see that the sine of this particular, trigonometric or this specific sine ratio is going to be given as 1. Therefore, we are going to have this specific equation given in that specific format. Let's assume this is going to be our equation 1. And therefore, our equation 2 is going to give us the maximum force which is going to be expressed due to the interaction of the forces which we have given, or the interaction of the fields which we have given in that particular case. Therefore, we can find the minimum force in this particular case. And the minimum force is going to be achieved when the angle between this specific field and this current carrying conductor is going to be 0. And in that particular case, this is going to be parallel to this specific direction. Now, in this case, we had mentioned that for the maximum force to be achieved, this is going to be perpendicular, implying it's going to interact at 90 degrees. For this one, for the minimum force, this is going to be the sine of 0 degrees, and therefore this is going to be equivalent to 0. Therefore, we expect the maximum force to be given, the minimum force to be given in terms of I, L, B, the sine of 0, and this is going to be giving us 0. Therefore, implying that the minimum force is going to be given in terms of that specific amount, which is going to be 0. Now, there is standard units which are going to be used in trying to measure this specific force, and this is going to be given in terms of what we refer to as a Tesla. Now, in this particular case, I can just give an example of these specific units which we are going to use in trying to quantify the magnitude of a magnetic force. And in case we come across them, of course, it will be easier for us in trying to identify which are the particular units which are going to be convenient for us. Now, in this particular case, the SI unit for the magnetic, force is referred to as Tesla. And in this case, this is going to be given as capital T, given as such. Now, this Tesla, we're going to see that 1 Tesla is equivalent to, of course, 1 Newton Ampere per Ampere per meter, given as such, or is equivalent to 1 Newton per Ampere per meter. And kindly check these specific dimensions which are going to give in terms of this. In case we have a problem in any of this, kindly comment on our comment section so that we can be able to do a follow-up. Now, in this case, this is going to be a conversion units for other dimensions and this aspect of, or derived aspect and this particular aspect of Tesla. And therefore, we're going to see that in case we come across these specific units, dimensions, we're going to identify them appropriate. Now, there are other units which we are going to come across being used in trying to, of course, quantify this magnetic field. And these are examples of Weber per meter. And this was named in honor of this specific, German physicist by Wilhelm Edward Weber. And as we're going to see later, this, of course, can be given in terms of a conversion, whereby we're going to have 1 Weber per meter. So this is going to be 1 Weber per meter square, whereby we are going to have per square meter given as such, whereby we're going to have 1 Weber per meter square equivalent to 1 Newton per Ampere meters, which is equivalent to 1 Tesla given as such. And then we're going to have, so this is going to be the other, of course, the derivations which we're going to use for this specific magnetic field. So we can have the second one, which is going to be given in terms of Gauss. And these units of Gauss are basically, as I had mentioned earlier, this is in honor of Johann Carl Friedrich Gauss, who was a German scientist, of course, whom we're going to come across in various aspects of mathematics and sciences. So in this case, 1 Gauss is equivalent to 10 raised to negative 4 Tesla. And this as well is equivalent to 10 raised to power 4 negative 4 Newton per ampere meters. And then lastly, we're going to have this one equivalent to 10 raised to negative 4 Weber per meter square. So these are some of the conversions which we are going to come across in measurement of this magnitude of magnetic force. And in case we come across them in our various discussion, and therefore that's going to be, of course, elaborate for us in trying to find, of course, what basically they entail. Now, in this case, we can just do a small evaluation test for us in order to find a way of representing this magnitude of a magnetic field, and that's going to form our final bit of this specific discussion on finding the magnitude of a magnetic field. So I'm going to read, we extract the information so that we are going to employ our formula in trying to find the solution to this one. So the wire carrying a current of 40 amperes, so I'm going to read this. The wire carrying a current of 40 amperes, so we're going to have a current given as 40 amperes, has a length of 15 centimeters. So we're going to have 15 centimeters as our length. Between the poles of a magnet at an angle of, so we're going to have an angle of theta which is 60 degrees, and then 60 degrees. The magnetic field is uniform at 0.08 Tesla, so we're going to have the magnetic field given in terms of B equivalent to 0.08 Tesla, and then we are required to calculate the magnitude of the force in the wire. So in this case, I'm going to read it again so that we are at bar with each one of us. So the wire carrying a current over 40 amperes has a length over 15 centimeters between the poles of a magnet at an angle of 68 degrees. So this is the length of the wire, and this is the angle of interaction. The magnetic field is uniform at 0.08 Tesla. Calculate the magnitude of the force in the wire. So we're going to use our formula of finding the magnitude of the force as we are given equivalent to the product between current, the length of the wire, the magnetic field, and then the sine of the angle between them, or the sine of the angle of interaction. And this is going to be given as a force is equivalent to the current, which is 40 amperes. And then we shall have a length, which is 15 all over 100 in terms of meters. So I've done a direct conversion for this one, times 0.08 Tesla, and then we shall have this one as the sine over 60 degrees. So in this case, we are going to see that this one basically is going to have it given as 0.46. Kindly, in case you find a different value, note first in the comment section as well, we'll say. So this is how we're going to treat the various subsequent evaluations which we're going to come across, especially on the concept of magnitude of magnetic force and other subsequent question sets. So that's it for now, guys. Kindly subscribe and engage us in the comment section, and also ring that notification bell to be getting updates on our various uploads. So that is it for now, guys. Bye, God bless you. Catch us in our next video.